Hello everyone. Today we are going to learn analysis of variance. In the analysis of variance, what we usually do is that if we have the variances, then we try to partition the total variation so that in the set of data where we have different sources, so that we can identify those variances, and then we can eventually analyze if we have multiple groups, then in those groups whether the means, that means in each of those groups the population mean we will get, whether they are actually similar or not. Eventually whether the population means, that means those groups are similar or not. So previously you learned using two population means, that means we tested using Z or using T based on the objective and then based on the available information. So we tested whether those two population means are equal or not. You also tested for a single mean whether it's actually 0 or other values. But in these cases, what we will do in the analysis of variance is that we will try to see whether if we have more than two population, that means 3 or more, then we will try to see whether those population means are actually equal. That means there is no difference between those populations means. And then if we find that there is a difference, then which one, that means which two population means, or maybe we could have more pairs, which population means are actually different. So we would try to find that in the analysis of variance. So our objective is to do two one-way or two-way analysis of variance. So let's say we have one factor, then we would do one-way analysis of variance. If we have two factors, I will talk about a little bit later about that, then we can do two-way analysis of variance. We will also test at first the equality of variances. That means if we have the population, several populations we have, then there the objective we have regarding a variable, whether their variances are equal or not. If the variances are equal, then we can proceed for the testing the multiple means, whether they are equal or not. We also like to do compare several means using some techniques. So I will also talk about that. Let's talk about one-way classification. So in the one-way classification, we have multiple population, more than two, and then from each of those population, we are randomly selecting the observation. And then you can see that we are at first talking about completely randomized design. And then what we have, let's say we have K population, 1, 2, 3 up to K populations. And we are assuming these. That means within there, we have observations we have are independent. Also in each of those population, we have means, mean 1, mean 2, and then you can see the population means, and they are actually randomly distributed. And if we calculate in each of those population variances, the population variance, then variation among them should be similar. So you can see that we have common variance. That means the population we are getting from them are similar. If they're not similar, then we cannot perform one-way classification. That means the analysis of variance. So what I will try to do, rather talking about theories, I will try to give you step-by-step procedure how you can perform the one-way classification and how you can actually perform the analysis of variance, then compare the means, and then how you can also compare the variances and the pairwise test for those means. So I will use this example. So in this example, you can see that we have treatments, only one factor. In one factor, we have you can see that 4 kinds of treatments for on mortality of logical time, and we have 20 plots altogether. In each of those plots, we apply those treatments randomly, and we have 5 randomly selected plots. So you can see that we have treatments A, B, C, D, and then we selected 20 plots, but then again we randomly allocate treatments into those plots. Let me draw that. That might be easier for you to understand. So let's say we have let's draw that. Let's say we have 20 plots, and then let's say we have selected those 20 plots randomly, and then let's say we have plots here, and then plots here, maybe somewhere here, somewhere here, here. Let's say we have 20 of them. Then we randomly assign those 4 treatments in those plots. Let's say this is plot 1, 2, 3, and up to 20. And then randomly we say that, let's say this one is getting treatment A, this one is getting treatment A, and then we have no bias which plot is getting which treatment. Let's say this is B, and then this is B, and let's say this is D. After we do that, then we observe them and collect the information, and after collecting them, then we created a table in Excel, and then we listed them. Okay. So what we try to see in here is that, let's say we have 100 seedlings. That means those 100 seedlings in each of those in those plots, and then after we actually observe them for a number of years, then we try to see that how many seedlings were dead. That's what we counted. So that's what we actually wrote down in here. Okay, so we have 4 treatments. For in each of those treatments, we try to see that how many seedlings were dead. That's what we listed in here. Okay. So side by side, what I will do, I will try to show you how you can perform the test in the analysis of variance in an Excel file. Okay, let me show that. So you can see that my objective is to perform analysis of variance, and this is one-way analysis because we only have one factor treatment. If we have more factor, another factor in this side, then we would say 2 factors. That means two-way ANOVA. But we have one factor in here, treatment. So I copied everything what I got in that example, and then I listed them in here. So we have 4 treatments. So our hypothesis is that from each of those treatments, the population mean would be similar. So that's what I said in my null hypothesis. In my alternative hypothesis, I said that at least 2 of them, that may be AB or maybe CD or maybe AD, at least 2 of the means are not equal. So that's what I would like to test. So I said that previously you tested 1 mean or maybe 2 means, but you never tested more than 2. So that's what we would like to do in the analysis of variance. Okay. So we have to do some calculation. So whenever I perform any ANOVA, then what I like to do is that I try to do some calculations before I proceed for the analysis. So you can see that at first I try to see in each of those treatments how many observations we have. So you can see that we have sample size 5, sample size in each of those we have sample size 5, and then all together the total measurements we have is 20. So that means if I sum these sample sizes in each of those treatments, then I got 20. Be careful about these notations. And then total number of groups, that means how many treatment groups you have. So you can see A, B, C, D, that means we have 4 treatment groups. After that, I try to sum these observed values, and you can see I try to find the sum of each of those treatments, and then sum of squares, that means if I square 10 each of those and sum them. So you can see that I squared them and then sum them. That means 10 square, 16 square, 12 square, 12 square, and then I sum them. I did the same for each group. When I sum them, I also try to get the total sum. So you can see that when I sum them normally, so you can see I sum these values, then what's the total if I sum them all? So that one, I write them in here. So that's the 257 is the sum, the grand total, that's what we call. This is not square. Sorry. This is not square, so sometimes I would like to find what's the square of this 257. So that's what we call the 257. Let me actually... Okay, so I corrected it. So you can see that whenever I sum them all, so that means I sum all of them. What's the total of all observed values? That's what we call T dot dot. That means, so the dot we used, let me define then why I use the dots. So the dots I used, so you can see the dots I used, 2 dots I used because 1 dot is coming from the treatments, treatment A to D. So that's what I'm defining by I. So I is from 1 to 4, or you can say A up to D and then B. Okay. And then the first dot is for the treatments, that means treatment A to D, and then the second dot is for each of those observed values. So that means we can say that T of or Y of I and J. So anytime we can say that the observed value for treatment A, and then we can have the all observed values. So you can see that the sum of the observed value, so you can see that I wrote T I dot, so that means the treatments A, B, C, D up to D. So in each of those cases, what are their total? So T will be used as total, Y will be used as observed values, and then you can see that for variances we also use SI. That means in the treatment A, treatment B, treatment C, treatment D, I define them by I because we have 4 options there. So the total sum for all these values, that's what I'm calling it T dot dot, because I am including everything. If I was including only treatment A and then all the values, only treatment A, all the values, then I would say TA dot or T1 dot. So that means this is the one. But I'm actually including all. That's why I said T dot dot. Okay, so let's go back. So over here you can see that, so I try to calculate all of them first. So you can see that I also calculate the squares, take the square of each of the values and sum them. After I sum them, I also sum for each of those treatments, what's the sum I got, then I actually find the sum of them, of those four values. And then for each of those treatments, so in assignment 1, also in first few lessons, you also calculated if we have several values, then how we can find the variance for them, the sample variance. So that's what I did. I calculated the sample variance for each of those groups. I also tried to find for each of those group, treatment A, treatment B, treatment C, what's their mean. That means mean values. And then you can also see that I tried to see that if we have the mean, then how about the total mean? That means if I take this total value divided by how many observations we have, that means the total means I try to find. Okay, so if you perform any analysis of variance, maybe it will be useful for you if you find all these values at first. So this one is actually square of the grand total. This is what we call grand total. And then after that, it would be helpful for you if you try to find what's the total sum of square. Total sum of square, it's easy to calculate. So you can see that we already found what's the, if I take the square of each of those values and sum them. So for each treatment groups, I try to find them and then sum them. So that's the value we have at the beginning. And then you can see that the grand total square divided by how many observations we have. So that means the treatment, how many treatment groups we have? 4 treatment groups. And then in each of those groups, we have 5 observed values. That's what I calculated in here. So you can see the total sum of square. So that's what we define by SST. Total sum of square. So I take on those values and then find the total sum of square. Similarly, you need to do another calculations, the between treatments, the sum of square between treatments. So since we are trying to find the sum of square, none of these values will be negative, all will be positive because we are trying to find the squares of them. For the between treatments, that means between those treatments, what's the sum we have? So all you need to do is to use this equation. So in this equation, let me read it for you. So in this equation, what we have is that, so you can see that for each of those treatments, 68 square plus 42 square, 85 square, 62 square. So you have to take the square of them, then sum them and divide by how many sample size you have. Each of the cases we have 5. And then that's the same thing we calculated in the total sum of square. So that's what I did. So you can see that I take the squares and then divided by sample size. Since we have the sample size in each of those treatments are same, then we can just divide it by n. So I will also show you if we don't have the sample size same, then how we can calculate them. After that, then we need to calculate within treatments. So within treatments, the sum of squares will be, if you take this total sum of square minus the between treatments, then you will find that the sum of squares within will be this one. So this one is easy to calculate. 302 minus 188. Our main goal in here is to find this table. This is what we call the ANOVA table. So in the ANOVA table, the sources of variation, that means whenever we try to find the differences among means, we want to test that how much variation we have, we need to figure that out first. That means we could have variation between treatments. That means treatment A to treatment B, we could have variation coming from there. Or we could have another variation, that means within group, that means within the observed value. So you can see the within treatment we have the observed values. So we could have variation, that means they could be different from each other. How much variation is going on, we also need to account that. So in here we have two kinds of variations going on. One is the between treatment, how different they are, and within the observed values. So that's why the sources of variance, you can see that the between treatment and within treatments we have, and then we sum them. So the degrees of freedom, we need to find that is that between treatments, since we have the how many treatments we have, k number of treatments, that means 4 treatments minus 1, and then the within treatment, the total number of observed values minus the how many groups we have 4 groups, and then total degrees of freedom will be how many observed values we have minus 1. Sum of square, we already calculated that sum of square, so you can see that I added them. Sum of square for within group, and then sum of square between groups, and then mean square is the, you have to take the sum of square divided by degrees of freedom. Same thing for within group, within treatments. And then the f value, since it follows the f distribution, the f value would be, if you take the between treatments mean square divided by the within treatment mean square, that means the values you found here, if you take the ratio of them, that's what we actually, that's the f statistics value we have. And f critical value, that means what we will be using to make a decision whether the null hypothesis is rejected or not. So you have to use the in the numerator we have these degrees of freedom, and the denominator we have these degrees of freedom. Using them, you have to use the f table so that you can find what would be the f critical value. So we are using the level of significance 0.05. Okay, so this one is easier, so you can see that how I calculated them. So I took the degrees of freedom for them, so you can just add these values what we found, and then we calculated them before, and then if you 188 divided by 3, 113 divided by 16, that's how I got them. F computed would be 62.98 divided by 77.1. And F critical value, so what I use is that if we have level of significance 0.05, and then the degrees of freedom would be 3 and 16, then you will find that the F critical value is 3.24. So what do you think? Are we going to reject or not reject the null hypothesis? So you can see that the computed value is way higher than the critical value. So that means if you draw the distribution, you will see that since it is higher, then we are going to reject the null hypothesis. The rejecting null hypothesis, that means the at least 2 of the means are not equal. That means they are actually not the same. So maybe 1 pair or 2 pairs or multiple pairs of treatment means are actually different. So that's how you can test multiple means together, and that's what we call one-way ANOVA, because we have only one factor treatment. In this example, all the sample sizes in each of those treatments were 5. That means they were similar, they are the same in sample size. But how about if we have unequal sample sizes? So in this example, you can see that we have the same number of treatments, but we have 4 observation, 4 sample size, 3 sample size, and then 5 and 5. That means the sample sizes are not equal. In that case, everything else would be similar. Only thing is that whenever we have the between sum of square, then what you need to do is you need to take the square of them and then divide by how many sample sizes were there. You can see 27 square divided by 3. So that's what we need to do. So you can see that that's what I did. So I used the how many sample sizes were there. And then when I calculated, let's say, the degrees of freedom, so you can see that the degrees of freedom I used previously k and then n minus 1, but in this case I used n minus k. That means how many observed values we have minus the treatment, how many treatments we have. That's what you have to do. So that means we have 17 observed values minus 4. That's the only difference I can see between the equal and unequal variances. Okay. Now I would like to talk about how we can find the confidence intervals for the treatment means. So that means if I want to know for each of those treatments, so let's say treatment A or B or C or D, for each of those treatments, if I ask you to find what is the confidence interval for the treatment mean A, then what you need to do, you need to find this table first, this ANOVA table first. After you find this ANOVA table, then you can use that. So to find the confidence interval for any of those means, you need to follow these steps. So at first we need to find what's the mean. That means which group we are talking about. Let's say we are talking about treatment group C, and then for the treatment group C, what's the mean of the treatment group C? So you can say at first the mean, and then we have to use the critical value. So you have to use T critical value, since this is one single mean. For single mean, you know, previously we have to use the T distribution. And then for the T distribution, what would be the value? I would like to show that. Also, you need to find the standard error of that mean. To find the standard error of the mean of that specific treatment group, then you need to use the ANOVA table. So in the ANOVA table, what's the mean squared error? This is the MSW, what you found. That means mean squared error. So that's the value we have to use. And you have to divide by what was the sample size in that group. That means we are talking about treatment group C. You have to use the sample size 5. So what I did is that I took the mean squared error 7.1 divided by 5 and took the square root. That's what I found, 7.1. That's a similar thing. You will see that on our ANOVA analysis. So that's the steps I followed for calculating finding the ANOVA table. So you can see that's the ANOVA table we have. And then now I'm trying to find for each of those mean what would be the interval. So that's what I'm trying to show you, how we actually calculated each of those. So we found the standard error of mean, and then we know the mean of treatment C, group C. The mean of treatment group C is 17, and then 1.19 is the standard error of the mean. Now we need to find what would be the T value. So T value, since we are using two-sided test, it's not a test, it's the confidence interval, but in the confidence interval we have to use the both side. So that's why you have to find for two-sided what would be the T value. So T value you need to find using this formula. So you can see that the level of significance by 2, that means 0.025 and 0.975. And then what you found in the within treatments was the degrees of freedom was there, n minus k. So you can see n minus k. So I used n minus k, and then I found n is the total observed values. That means total measurements, number of measurements we have. 20 minus 4, that means 16. So I used 16 is the degrees of freedom, and then 0.025, or in the table you will see that 0.975. Yeah, you can find 2.12. And then treatment mean was 17. That's what I showed. So what I did, I just used these values, 17 minus 2.12 multiplied by 1.19. So that's the lower limit. And then the upper limit is 19.53 because I used 17 plus 2.12 multiplied by 1.19. So that's the upper limit and lower limit I found. So for the confidence interval for the difference between two treatment means. That means we are talking about two treatments means, two groups. So let's say we are talking about finding 95% confidence interval for the treatment groups C and A. So that means at first we need to find the difference between them. So you can see that I found the difference between them is the, I use their means. So you can see the C and A. So I use this C and A means. So I calculated their difference first. Sorry, the difference first, and then I like to find what would be the standard error of the difference between those means. So you can see that if you have equal sample size, so you can use this formula. If you have unequal sample size, that means you have to use each of those sample sizes. If you have equal sample size, that means the sample sizes are same. That means you can just divide by the number of samples you have. So we have equal number of sample sizes. That's why we are going to use this one. And then we can see that similarly what we used before, mean squared error divided by sample size, since we have two of them, so we multiplied by 2. And then I got this value. So 2 multiplied by mean squared error divided by sample size, and then so take the square root. And then I just use all these values I found. The difference between the sample means 3.4 minus the t value is same what we found before, 2.12 multiplied by their standard error of difference between means. Okay, so that's what we did for finding the 95% confidence interval. If we have, let's say, 99%, then you have to change the t value only. If we have 90%, then you have to change the t value. Okay? That's the only difference you have. So in the assignment or maybe in the exam, you will see that I'm asking you finding the difference between two groups. Then you can follow this example I showed you. So that's what I tried to show you in that example, how you can find the 95% or any confidence interval for any pair of treatments or pair of the groups you have. Then you can find that. So let's recap what we learned. So we try to see how we can perform one-way analysis of variance, and then using this example I showed you how you can test the multiple means, whether they are similar or not, and then how you can calculate each of those sum of squares and then find this ANOVA table. After finding that, I showed you how you can find the confidence interval for single mean or pair of means. So that's it for now. Thank you.